In this part, we are going to talk about thermodynamics and kinetics in the reactions. So when we talk about thermodynamics, we are looking at the stability. So thermodynamics is the study of relative energy levels of the reactants and the products. And we already talked about it. Something that is lower in energy means more stable, and something that is higher in energy is less stable. However, kinetics is the speed of the reaction, and basically we want to know which product is formed first. Sometimes in reactions, you may have multiple products. The one that is forming first is the kinetics product, and the one that is more stable is our thermodynamics product. If we plot potential energy versus the reaction coordinate, there are two possible pathways that the reactants can react. In the first pathway, which is the red pathway, and it has a lower bump, we can form E and F products. However, through the blue pathway, which has a higher maxima, we can form C and D products. So there is a different energy barrier that we need to pass through to get to either of these products. One of them has higher barrier and the other one has the lower one. So the one that has lower energy barrier can form the products faster. So it will form the kinetic products. Therefore, E and F are our kinetic products. However, if you compare the energy level of C and D products with E and F, C and D are more stable than E and F, so we call them our thermodynamic products. So basically, the more stable products are our thermodynamic products, and the products that can pass through this energy barrier faster are our kinetic products. In this specific diagram, the formation of kinetic or thermodynamic products is dependent on temperature. At low temperature, reaction can form the kinetic products. However, at high temperature, it can form the thermodynamic products. So why is that? Because at low temperature, there isn't enough energy for the reactants to pass through the high energy barrier here. However, the energy is sufficient enough to help the reactants to pass through this lower bump to form the kinetic products. Now, if we increase the temperature, we are providing more energy for the reactants to jump over this high energy barrier and form the thermodynamic products. So in this example, at low temperature, we are forming our kinetic products, and at high temperature, we are forming the thermodynamic products. Sometimes we have reactions that both kinetics and thermodynamics products would be the same thing. For example, products C and D here, they are more stable than E and F, so they are thermodynamically favored. Also, C and D are kinetically favored as well because the energy barrier here is lower comparing to energy barrier to reach E and F. Therefore, C and D are both kinetically and thermodynamically favored product. Negative sign for delta G tells us a process is spontaneous and the products are favored. However, that doesn't tell us anything about the rate or kinetics for that reaction. So we have some spontaneous processes or reactions that are very fast, such as explosions. And we do have some spontaneous processes that are very slow, such as conversion of diamond to graphite, which takes millions of years, although it is a spontaneous reaction. Since we talked about kinetics, we need to learn about rate equations as well. We are going to use these in chapter 7, where we learn about SN1 and SN2 reactions, substitution reactions basically. But here we are solely talking about the rate of the reaction, and the rate equals the rate constant multiplied by the concentration of reactants. So this is not dependent to the product's concentration, because it's related on how fast reactants can react with each other, not the products. So reaction is the result of collision between reactants, and if we increase the concentration of reactants, it will increase frequency of the collision, so they are colliding more, therefore the rate of the reaction would increase. Also, the rate equation might have different orders. An order is basically the degree to which a change in concentration of the reactant would affect the rate of the reaction, and we are going to talk about them in the next slide. We have different orders for the rate of the reactions. In the first order reaction, the rate equals the rate constant times the concentration of one of the starting material. So it doesn't matter how many reactants you have, A, B, C, the rate is only dependent on concentration of one of them. So if you double the concentration of A, the rate is doubled. But if you double the concentration of B, the rate stays unchanged because the rate is not dependent on concentration of B. So a very good example for the reaction that has first order rate is SN1 reaction. We are going to talk about SN1 and SN2 reactions in chapter 7. Now, in the second order reaction, the rate is dependent on concentration of two of your reactants. So if you double the concentration of A, the rate is doubled, and also if you double the concentration of B, the rate is also doubled. So a good example for this type of reactions is SN2 reactions. In the third order rate, one of the reactants have more impact. So if you double the concentration of A, the rate is quadrupled, but if you double the concentration of B, the rate is still doubled. So one of them has more impact comparing to the other one. The reaction rate is the function of number of collisions that can occur during the course of the reaction. And the rate is affected by some factors. The first one is the concentration of reactants. So we already talked about it. According to the order of the reaction, the concentration of the reactants can have different impact. We also have other factors to consider, which we are going to talk about in the following slides. The next factor is activation energy, which we show that with EA. So basically this is the energy barrier between the reactants and the products. So basically the minimum energy required for the reactants to collide and form the products is activation energy. So if a collision between reactants doesn't have enough energy to overcome this barrier, the reaction will not occur. Therefore, the lower the activation energy, the larger number of molecules can form the products, so the reaction would be faster. The next factor is temperature. So at higher temperature, a larger number of molecules would have enough energy to jump over the activation energy barrier and form the product. And the last factor is steric consideration. So we already talked about the steric hindrance. There are some cases that basically the reactive side of the molecule experience steric hindrance by presence of a large group in its neighboring carbon, which can impact the frequency of the collision. And we are going to talk about this in chapter 7. The last factor is catalyst. So now what is a catalyst? It is something that you can add to the reaction to speed up the reaction, and it helps the reaction by lowering down the activation energy. So catalyst basically provides another pathway for the reaction, different from the original pathway to lower down the activation energy. If you look at this diagram right here, the original pathway for this reaction had very high activation energy. However, when you add the catalyst to the system, the activation energy is lower, which helps with the speed of the reaction. Now, the key point here is that the catalyst is not consumed in the reaction, even though it is used in it, but you can get it back at the end of the reaction. For example, an alkene can react with acid to form the alcohol, So basically we add OH to the more substitute carbon. So it has two substituents, this one has one, this is more crowded, we add OH to that carbon. And we can get back the acid at the end of the reaction. So acid is a catalyst in this reaction. It helped with the reaction and we recovered it at the end. Again, I would like to emphasize on the concept of kinetic and thermodynamic products. These concepts are very important in organic chemistry. So again, I would like to mention their difference. The formation of kinetic products is determined by the energy barrier, which we call that activation energy. So the smaller the activation energy, the faster the reaction would be, therefore the kinetic products can form. However, the formation of thermodynamic product is determined by delta G, this energy difference right here. More stable product that is lower in energy, is our thermodynamic product. Another important concept to talk about is the difference between transition states and intermediates. Reactions often involve multiple steps. For example, this energy diagram shows 3 steps for a single reaction. So this is step number 1, number 2, and number 3. So every time that we passes through a peak, we have 1 step. So these peaks, we call them transition states, and the minima or the valleys, we call them intermediates. A transition state, as its name implies, is a state that reaction passes through, and we cannot isolate transition state. So transition state is a maxima and represents a transition as bonds are made or broken. However, intermediate is a species that formed during the course of the reaction. It is observable and it exists for a period of time before reacting further. To understand the difference between transition state and intermediate better, let's consider this example here. So imagine that you are jumping in the air as high as you can to reach a desk while your friend taking a photo of you. So when you reach the highest point, basically you have a photo of yourself. However, it is not true to say that you were able to spend a considerable amount of time at that point. But there is a photo of you that you are passing through that state. So we call that transition state. Now, when you reach on a desk, your photo is different from the previous one, and it's actually possible to stand on a desk for a short period of time. This is the intermediate point. So when you want to again jump to reach to the ground, you have to pass through another transition state and reach to the ground. So this is what's happening in the reaction. So when molecules want to form the product, they have to pass through a transition state. It is basically fleeting. They cannot be observed, the transition states. They reach the intermediate, a short period of time, which is observable, and again they need to pass through another transition state to reach to the product. A practice problem here. So we have an energy diagram and we need to answer a few questions about that diagram. So the first question is asking which locations represent intermediates. We already talked about it. All the valleys and minimas, they are intermediates. So we have 2 of them. Therefore, point number 2 and 4 are our intermediates. The second question is asking whether the reaction is endothermic or exothermic. So to answer such a question, we need to look at the energy level of products and the reactants. So products are more stable than the reactants, therefore the process is exothermic. So we already talked about that. The third question, it is asking find the highest energy transition state here. To answer this question, the highest energy transition state is the one that has the highest activation energy. So the first step, which is this one, the activation energy starts from the reactant to the transition state. So this is the activation energy for the first step. The second step, again, it starts from point 2 to 3. So this is that activation energy. And the third one has this activation energy. So obviously step 1 has the highest transition state. And the fourth question is asking how many steps are in the reaction. So the number of transition states gives us the number of steps in the reaction. We have 1, 2, 3 transition states. So we have 3 steps. Next, practice examples. So we have a few diagrams in the left and we want to answer these questions about them. So the first question is asking which diagrams correspond with the two-step mechanism. So we already talked about it. The number of transition states gives us the number of steps. So obviously diagram B, we have 2 transition states, and diagram D, we also have 2. So B and D are 2 steps mechanism. Which diagrams correspond with the one-step mechanism? So we need to look for one peak or one transition state, which is diagram A and C. Compare all 4 energy diagrams which have a negative delta G. So for the negative delta G, we need to look at the energy level of reactants and the products. When the products are more stable, we have negative delta G. So in diagram A, products are more stable than the reactants, and also in diagram B, products are more stable. So A and B. Compare all 4 energy diagrams, which one exhibits the larger activation energy. So we need to draw the activation energies for all 4 diagrams. Activation energy starts from the reactants to the transition state. And this is the last one. So obviously the last one has the highest activation energy. Which processes will have a value of KEQ that is greater than 1? So when KEQ is greater than 1, the delta G should be negative. Okay, the process is favored, the reaction will occur. And we already talked about that. So diagrams A and B, they both have negative delta G, so KQ should be greater than 1 for both of them. And which process will have a value of KQ that is equal to 1? So when KQ equals to 1, that means delta G should be 0, meaning that we shouldn't see any energy difference between the reactants or the products. And only diagram C shows such a thing.